Anybody going to Rebellion this weekend?
I wanted to go to Friday.
The only person I know is 3 doors down. And a couple of others. There's very good. They're Skinner, yeah. But the tickets are like $200. So, okay. I know. They're yeah. They need to go to prom. I'm chaperoning prom. My husband is refusing to go. Oh, that's okay. He's already gone to Lake 2 with me. It's all good. So, okay, guys, ready? Here we go. I know you remember all of your nomenclature, every little ounce that we went over. Specifically acids, which were like the easiest of all of them, right? Totally. Okay, so I want to just review 1 or 2 just in case. Then you just took notes on the template of how to approach a binary acid versus a ternary acid. So first off, is this one binary or is this one ternary? Binary. When you say, how do you relate to me it's binary? What's the prefix? 2. No. The prefix is hydro. You just wrote this down in your notes, right? If you want to look back at your notes, go for it. If not, try to do it from memory. So you have to say it's binary by saying the term hydro. Hydro does not mean there's an H in the front. You're like, duh, there's an H in front of every single acid, so the hydro can't be the determinator of that factor. Okay, so then how do you end it if you're just simply trying to end a binary? Ic acid, right? So you have to say ic acid or what goes in between? It's like sulfur, sulfuric. It's kind of weird on like specifically which way we choose to do it, but it's actually sulfuric acid. So hydrosulfuric acid. Okay, so hydrosulfic acid sounds fine to me. I know what you're saying. This one is not binary, so what do we not say? We don't say hydro. We just go straight to the chase. We take that polyatomic ion we see. Which one do we see here? We see sulfate, right? We see the SO4 2-, but we can't say sulfate. We say sulfuric, right? So if you want to say sulfic, it's fine. Sulfuric acid. And what's our stupid way of remembering that? Ic, IH image. So ic and H go together. This is sulfate and ic go together. Name, I'll have it on here, I think. Name this one. So that's got this sulfite. Sulfurous. So that's the sulfite. So that's sulfate, SO4 2-, sulfite is SO3 2-, and ites go to oses. And what's the stupid way to do that? Tendinitis. So that's just sulfur acid. And you always end in acid, and that the term acid is telling me there's an H in the front of this compound. The acids always have H pluses in the front of them. Let's do one more. Let's do this quad right here. Name this first one. I heard per. Okay, say it again. Perchloric acid, because that's perchlorate, which is ClO4. It's perchlorate. What's this next one? Just chlorate, which goes to chloric. And then what's the next one? That's chlor. So that's the chlorite right there. So we changed the name to chlorous acid. The last one. What means below? Like a needle that goes beneath your skin. Hypodermic needles, right? That's the way I remember it. It's a real great example. But it's hypochlorous acid. Hypo means below, right? So that's going to be one below that, one oxygen less. That's pretty good review. So which of these are the strong acids? You wrote them down in your notes just now. Which of these are the strong ones? Sulfuric, which one else? Perchloric, those are two of the ternary. There's one of the other one that's ternary is not on here right now. What is it? Say, I just heard it. Nitric acid, so HNO3. So if you didn't put the formulas down along in your notes, you might want to add the formulas. You may have challenged yourself and done that already, but I have the formula names. These are the formulas themselves. H2SO4, sulfuric acid, perchloric acid, nitric acid, HNO3. So those are the ternary strong acids. Which are the 3 binary strong acids? Hydroiodic, HI, hydrobromic, which is HBr, and hydrochloric, which is HCl. So those are the formulas for you if you'd like to add those to your notes. You good here? What is the term strong refer to? Ionizing completely, dissociating completely. What does that mean? Like if I have a glass full of sulfuric acid, okay, full glass of it, what would actually be in here? So I told you that I had sulfuric acid in here, right? Is that actually what's in here? Or, since it's strong, is it something that's related to it, but not exactly that? I'll answer this one for you. There's not actually sulfuric acid. Pure sulfuric acid is not what's in that container. It's actually just a combination of a bunch of H pluses and sulfates. Because whenever this jumps into water, for example, which is that container, they ionize 100%, meaning there's no such thing as this anymore. This will ionize pretty immediately to H pluses and sulfates. Meaning, if I took a microscope and I could really get down to the atomic level of the ions, I wouldn't find any of these pure sulfuric acids. I would find their counterparts. Now, if I had acetic acid, is acetic acid a strong acid? Acetic acid. Look on your list of 6. No. So this is so easy, guys. If they're on the list of 6, they're strong. If they're not, they're weak acids. So I can give you every other. I can give you unicorn acids and dog acids and anything, right? I can give you acid. If it's not on that list of 6, it's not going to be strong. So if acetic acid is H, what's acetate? C2H3O2. So remember C2H3O2, or how did I do it? Acetate, C2H3O2. There's 3 letters in that one, there's 3 syllables. That's acetic acid, okay? Acetic acid is not strong, so it will not 100% ionize like this one does. Instead, what happens is it can do both. It can ionize a little bit, and then it can revert back to its original form. So we draw a double-headed arrow kind of like that, or a 2-sided arrow. So it'll make a couple of these H pluses and a couple of these acetate ions. Thanks, Jordan. But most of it's going to be left here. So you might have 98% of the acetic acid left. Only 2% ionizes. It's a very, very, very low amount. So did you guys get to the part where you're writing weak acid stuff down? What page was that? I don't have my printed copy. Write down something like this under an area where you were noting the strength and the weak, strong and weak acids. It says like save stuff for Ka on my PowerPoint. So here, we'll write it right here. Let me see. It can be anywhere truly, but I'll give you a specific. My computer is frozen. Don't freeze. All right, problem people. Okay, so someplace write down the definition, the difference between strong and weak. And you can give yourself an example there. We'll go into more depth with that when we do actually get to our KAKB notes. I'm not gonna play with this because it's not like mirroring. So this is the definition of weak. Weak means not 100% ionization. So not ionizing at a large extent. This one's only ionizing about 2%. And so if I had a beaker of this, and you guys actually saw this picture. I know that picture was on there, where you had a combination of all 3 of these species, is how we call them. So we'll have some H pluses, C2H3s, O2 minuses, and then we'll have a bunch of these acids that never ionized. And so I'm not going to draw this 100 times, but I'm just going to put times 100 down here. There's a lot more of these than these because they don't ionize very often. Do you now notice the difference between strength or the strong and weak definition? It's not related to concentration whatsoever. It's not like, oh, it's a really strong, concentration of Kool-Aid. Strong Kool-Aid means really concentrated, right? That's totally different than the definition of strong for acids and bases. Okay. So let's continue. We're going to walk through a couple of these definitions some more, and I'll give you my cheesy ways of remembering everything. Because when I was your age, I was like, I can't remember the difference between Arrhenius, Bronsted, and Lewis. They all just get mixed up. They all relate to acids and bases, but I'll tell you how I actually remember that. Oh, before I do that. So this is the definition that's relating to strength, okay? First one's acetic acid, the second one's hydrochloric acid. Which one ionizes 100%? Hydrochloric. So if you're ionizing 100%, you make a lot of ions, right? Ionization, dissociation. So you make 100% H plus and CO minuses. This one makes like 2% or less of those ions, so we're just going to conduct better electricity better. Hydrochloric, despite the fact that the concentration is much, much, much weaker more dilute. That's 3 molar. If that's not ionizing, we're not going to get any ions. We're not going to conduct electricity. So this one still weighs. Okay, so let's look at definitions now for Bronsted and such. We just went over that. Here, I need to explain 1 or 2 things, then we'll move on from here before I get to definitions. So we have seen this reaction before. We've seen where the metal reacts to the acid, and we've seen the hydrogen gas be produced. So what kind of reaction is that? Single replacement, right? The metal replaces the H from the acid, and so it's a single replacement reaction. That's going to happen a lot because metals don't really care about their electrons. They're very willing to give up their electrons because the trends, right? It's got a low ionization energy. And so we've all experienced the beauty of acids before. They think of vinegar, lemon juice, anything like that. They're sour. They will burn your cuts and stuff on your fingers if you ever pick up a lemon wedge. It burns a little bit. And then additionally, information down here. When we talk about those things ionizing, we do use the term electrolytes a lot. So a strong acid we call a strong electrolyte. So if you want to add this anywhere, that would be good. Strong acids are strong electrolytes. And then guess what weak acids are, guys? Weak electrolytes. And the same can be said about strong bases and weak bases. And the reason that these are ionizing more readily than the weak ones is because the bond between the H and X, that covalent bond right there, is very, very polar, meaning one side has more electrons than the other side. Generally, it's going to be, the polarity is going to be pointing towards the X, so it's going to be the partial negative side on the X, which is the anion, and the partial positive will be over here on the cation, which is the H+. And so what happens is if this is really polar, it's very likely to just break. So if it breaks, what comes off on the side? What's on the side? The hydrogen. And so if you release hydrogens into water, you're an acid. That's it. That's the definition. If you release hydrogen ions, you're an acid. And then the bases on the other side, they're electrolytes, but on the opposite end of the spectrum, they make hydroxides. So this OH right here, do you remember that's hydroxide? Shake your heads, people. Hydroxides. Okay. So the hydroxides are what's creating the ion, and that's going to be considered a strong or weak electrolyte based on the extent of dissociation. Okay, there's a different foldable, slightly. I like our new style better. Okay, here's the fun part. So three different people are involved in making these definitions. Basically, they just watched and observed what they saw in water, and they're like, oh, if it turns the pH really low, makes a lot of hydronium, or H pluses. There's 2 different names for this. Okay, so hydronium is the one that we'll try to refer to most often versus just H plus. They said that's going to be what we call an acid. So Arrhenius acids always make hydronium in water. Arrhenius bases always make hydroxide in water. Well, how do you remember Arrhenius is the one that refers to water? What is water in Spanish? I know it's not 100% the same, agua, Arrhenius, but if you can remember some relationship between agua and Arrhenius, you can remember that's how they behave in water. So they're just describing how acids and bases behave in water. So if you need to write that down for yourself, do so. Second, so that was really, really narrow-minded, right? They're just looking at how it acts in water. So then Bronsted-Lowry, which is actually a combination name. Bronsted-Lowry were like, well, there's other ways to observe acids and bases. It's not just in water. So they're like, we're going to have to expand this definition. I need most of them. I need 15. Count them out. I'll have to check in a second. I'm sorry. Okay, so Bronsted and Lowry ended up saying there's more examples of where acids and bases can be used in real life, not just water. So here's how I remember this one. Bronsted acids are bad acids. Okay, so my 15-year-old self was like, yeah, that's how we're going to remember it. Okay, so Bronsted acids are bad acids, and they represent Bronsted acids are donors, BAD. Bronsted acids are donors. Donors of what? Protons, which the proton terminology is just saying I have an H plus that's able to be donated, okay? So this means donor, has a meaning behind it. The other one doesn't make as much sense. Bronsted bases, ba-ba, okay, they're acceptors. Of what? Protons, okay, so they have to pair together, they have to play together to make this work because the Bronsted acid has to give up this H plus to the Bronsted base. They have to occur together. And that's what you saw later on with conjugate acids and conjugate bases. They always go pairing up with another one. So this proton terminology is describing the H plus because look at your periodic table. Tell me the molar mass of hydrogen. Okay, so I hear 1.008. What does that consist of? What makes up the mass? What are the three subatomic particles? Protons and neutrons. Okay, so this is equal to protons plus neutrons, right? So atomic mass is made up of protons plus neutrons. Which of those subatomic particles is making up that one? What does hydrogen have? Hold on. What does hydrogen have in terms of its numbers, protons, neutrons, and electrons? One what? You say one of each, right? Most people are like, oh yeah, it's got one proton, one electron, because they have to balance each other out, and one neutron. But if they had one proton and one neutron, what would the mass be? 2. So it cannot have a neutron. So it's got one proton, that's all it has. So hydrogen having one proton and one electron with 0 neutrons means its mass is 1. Well, when you take away that only electron to give it that positively charged cation charge here, when you take away that electron, what's left? One proton. So why do we call hydrogen a proton? That's all it is. It's literally a proton left in the nucleus, and that's it. So a lot of times we'll call it proton, hydrogen ion, hydronium, H ion, stuff like that. It's got 3 or 4 names we will refer to. So Bronsted acids are donors, bad acids, how I remember it. It's up to you on how you do it. Lewis acids and bases we don't refer to as often, but where have you seen the term Lewis before? Lewis dot structures. Well, dot structures, those dots represented electrons. So it makes sense that Lewis is talking about lone pairs of electrons, not protons, not hydrogen ions at all. It's talking about how do the electrons interact. So acids are acceptors of lone pair in this case. In the Bronsted acid ones, what were the acids doing? They were donating protons. Well, in the Lewis definition, they accept electron pairs. They're opposite here. And then the bases are going to be then the ones giving or donating it. So this first example, image, here have a proton. You think, which of these definitions is it? Arrhenius, Bronsted, or Lewis? Bronsted Lowry, because they're donating a proton and the other one's taking it. It's just an exchange of protons. This one in water, making hydrogen ions, Arrhenius is good. Arrhenius is agua, water. And then the last one where you can see this lone pair being shared would be Lewis. Okay, next. We talked about this. Great. Okay, so our 8 strong bases. I wrote on y'all's paper, or on your notes, sodium. It starts at lithium. It's lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and then barium hydroxide, strontium hydroxide, and calcium hydroxide. So these right here, it kind of forms a B. I highly recommend you draw it like this, and if you didn't already, then do that now. But everything with the base is going to be considered a hydroxide. Well, that means they have to make hydroxides in solution in equal amounts, or based on the subscripts, it'll change up how many they're made. So for example, lithium hydroxide, so all of these are going to have OHs with them, right? Lithium hydroxide, when it dissolves in water, it ionizes to form lithium ion and hydroxide ion. Do not break up the OH, right? It's OH as a whole. So that means if I have 1 molar lithium hydroxide, I make, again, 1 molar of lithium and 1 molar of hydroxide. So a lot of times when we're looking at the acids and bases, we're concerned about the concentration initially and the concentration of the ion of interest that it makes. Well, this is the ion of interest that it makes because this is the thing that makes a pH basic. A lot of hydroxide, a surplus of hydroxide will make a pH towards the basic region, which is that 1 or 14? Basic is 14, right. So if we know that this one's making, from one lithium hydroxide, it's making 1 hydroxide, we say it's, again, 1 molar because that's what it started off as. It's a 1-to-1 ratio. Does that make sense? Okay, let's look at one that's not a 1-to-1. So which of these rows, which of these groups is going to give non-1-to-1? The second one, right? So what's the formula for calcium hydroxide? OH2, right. Ionize that one. CH2 plus OH minus. Where's the 2 go? As a coefficient, right? So that 2, saying there's 2 hydroxides means there's 2 hydroxides on the side as well. So this is where you wrote down about the strength of the bases. How does that play into the concentration of the hydroxide, which is towards the end of the notes with the pHs. So I'm kind of previewing that now. Let's say this is 2 molar calcium hydroxide. What would the molarity be if the hydroxide made? 4, because it's a 1-to-2 ratio, it doubles. This is going to be important to calculating pH, pOH, and some other variables in the pH side of things, calculations-wise. So this is only true for strong, I'm going to put dibasic bases, strong bases that are dibasic, meaning they have 2 hydroxides. That's not going to be true for anything acids-wise at all. Acids are what they are. Their concentration, if it's strong, it's 100% ionization. You make the same level of hydroxide or hydronium on the other side. I call them dibasic because they have 2 hydroxides. Okay, so that's what. I'm just gonna get that right now. What are you talking about? So these are the images that you saw. So do you realize the strength differences between the images? Like you could look at an image and tell me something's strong or something's weak. So like the way this is shown here, all of them are ionizing. So what do you consider that? Strong. But this one, you see one ionized and the other ones didn't. So you call that weak. Okay, cool. Conjugates we got to. So this is on your sheet. Let's work through a couple of these. They're right on the top. Jasmine and Matt, here, grab these. There's not one on here. I left one over there for you. Here. Pass one, Matt. Pass that to Avery. So please work with me here. What is the conjugate base? You guys have the definitions for these on your paper. So remember, conjugates are always going to be the product that came from the ester base as the reactant. So I'm going to pull this back up in just a second. I just need some space. So the first example, what is the conjugate base for each of the following acids? So what happens here is H2SO4. You want to write down these examples, okay? Don't just watch. Participate. It makes more sense to do that. So these are going to be represented. I'm just going to write them in water right now because I want to show you how they translate between themselves and water. I'm looking at the very first one that says, what is the conjugate base for each of the following acids? H2SO4. So it's just like an above example, yeah. So I'm going to add this to water. And I want it to react. Well, which of these do you think is going to be the better acid? Sulfuric acid or water? The acid is going to be the better acid, right? So sulfuric acid, right? This is the acid. What do acids do? What do bronzed acids do? Donate what? A proton. Okay, I'm going to show the donation of protons. So it's like, all right, here you go. Bouncing this little guy over here. So the proton's being donated. So now it has lost one of its H pluses. I'm just going to lose one right now. I could do both of them. Let's just do one at a time. What's left over here? HSO4 charge. Remember, if you are donating an H plus, what do you become? You become a negative charge because that plus was a part of you. And when you take the plus away, you become one less, so one negative. So it's HSO4, one negative. And then what does this guy become? H3O plus, because the plus is coming to you, so you must gain that charge as well. Okay, so here's the whole shebang, guys. Here's the reaction we're looking at. We already knew the acid was donating. What does it donate to? What's the counter thing? So Bronsted acids donate to Bronsted bases. Okay, so they always pair together. So Bronsted acids donate to Bronsted bases. So this will be our base here. Okay, and then our definition for, I'll come right back down here, okay? Our definition for, let's just do the conjugate bases first, okay? They come from acids. So conjugate bases, I'm going to call those CV. Those come from acids. So this guy here made which of these products? What did it become? The first one or the second one? The first one, because you see how similar these are? They're only different by 1 H plus, right? So this guy became this guy. There's just one difference. There's one less H plus. So we say the acid makes the conjugate base. So we would then label this one the conjugate base. And then separately, water became what? What is this called? Hydronium, right? That's called hydronium. So water becoming hydronium means the base, water's acting as the base in this case, became the conjugate acid, okay? And that's because your conjugate definitions say acids originally make conjugate bases, and bases originally make conjugate acids. Can you identify a conjugate acid and a conjugate base from a reaction? You're like, not sure, let's try. Okay. So look at the ones right below it. I'll do the first couple with you, and then let's try from there. The first one says acetic acid plus water yields acetate, or no, sorry, yields hydronium and acetate. Format is very similar here. Okay, so as you can see from start to finish, what happened to the acetic acid? What did it do as it became this? It what? Give me some terms that relate back to our definitions. It what? It donated a proton. Do you see the lack of proton from here to here? Yes, you're like, what did it do? It donated it. So if you donate something, specifically an H plus in this case, you are called an acid. You are the acid. So if you make something else, what do acids always make? Conjugate bases. You got to put CV. It has to be called conjugate, so you're identifying it correctly. So that means if poor old H here had to donate its proton to water, water is acting because it's accepting the H plus, right? So if you're accepting the H plus, you're called a acceptor, which is a base in this case. That's Bronsted base. So Bronsted bases accept the H plus, and you can see the evidence of it because look, it's got an H plus here. It didn't have it before. So bases make conjugate acids. And I'll tell you why we call it conjugate acids and conjugate bases. What if I totally reverse this reaction? What if I reverse and everything goes backwards? Which of these has the extra H plus to donate? This guy. Do you see an extra H over here? No, this H is a part of acetate. Do not take it. Don't even look at it, people. Do not take it. It is acetates. That's just a free H. It's like, here, do what you got to do with it, okay? So this one's got the extra H. So what is it going to do? It's going to donate it back to acetate so it can re-become acetic acid and just plain old water. So that's why they're called conjugate acids. Basically, if you reverse the direction, this one acts as the acid, and that one acts as the base. Some of it's making a little bit more sense. Okay, now you're like, oh, that's why it becomes something else. It's not becoming something else. It's literally acting or describing how does it behave with something else or in water or with ammonia. I mean, I can keep going. Let's do another one. What happened? Oh, gosh. What have I done? Okay. Let's do that one underneath it. It's a little bit more difficult. HCl. Hopefully you're going through here with me, okay? HCl plus SO3, 2 minus, yields HSO3, 1 minus, and Cl minus. Work with me here. You should be working with me. Thank you. Okay, so who wants to tell me what are you observing here? Over, Lena. So what's hydrochloric acid doing? How do you know it's giving up a proton? How do you see that happening? You're looking into the future. Yes. What do you see? Right, so you're seeing that hydrochloric acid has lost a proton because it's over here as chloride, which means I'm lacking an H+. So it obviously donated, right? No, with no question. So that's the acid, right? Well, what does this have to be then? This has to be the base. If you're accepting a proton, you are the base. And you can see the evidence of that because now we go from sulfite to bisulfite here. So then what would this one be called? Yes, conjugate acid. And then what would this other one be called? Conjugate base. All right, guys. Do the one that is the ammonia, which is, ammonium. You guys do this one and we'll move on from here. NH4, 1+ and carbonate, making ammonia, and HCO3, 1-. It's the upper, it's the one on the top of the next row. And Avery, I want you guys to do your labeling. Oh, you guys need to want to open this. You turn my back and all right, Niall, what you got for me, man?
Oh, I said that the ammonia was the acid.
I like that you said ammonium. Ammonium, you're saying is the acid, right?
Yeah.
Why?
Because I can see that it lost an H.
Right, you can see the difference of 1H. So you lost it, so you donated it, right?
Yeah.
So what is this one?
That's the base.
And so this is the,
Yeah, conjugate base.
because these are connected, acids make conjugate bases, and this one is
The conjugate acid.
because the base makes the conjugate acid. Okay, so we got our definitions, we got our examples of how to determine conjugate acids and conjugate bases. Generally, ammonia, NH3, is considered a base, and that was on your definition up here. Okay, so generally, ammonia accepts an H+. Let's do it in the form of hydronium. So if I'm telling you ammonia is a base, I want you to tell me what the product is. So I heard an H4, what? Plus, because if you're gaining an H, I say H, but we all know that means H+, sorry. Hydronium ion, H+. So you're getting that H+, you're becoming ammonium, and then what's left over from here? H2O. Not minus, actually. This, there's like a number line, so you go from plus to 0, and then negative. So you're stopping at 0, which is neutral, which is just water. Okay, so we can actually predict ours as well. Not only like write it out, but we can predict. Okay. So let's watch a quick video on the pH scale, which I find interesting. I find interesting that they used it originally to make sure they didn't kill their customers. This Danish beer company, they were like, we should probably test like the acidity of this before we serve it and sell it. And they're like, oh, well, this is going to kill our customers, so let's see what we can do to adjust this. So they revised it in 1924. So a piece of American history there. Actually, Danish history. Danish history. Okay. Write down a couple things for yourself.
Hi, it's Mr. Anderson, and in this video I'm going to talk about acids, bases, and pH. If you ask people what pH measures, they'll usually say if something is an acid or a base. And they might know that water has a pH of 7, that acids are generally lower than that, and bases higher than 7, but that's where a lot of people's understanding ends. And so I kind of want to explain to you what pH is and how it's determined. But before that, I want to tell you why it's important. I'm a biology teacher, and so everything kind of goes back to life. And so this is a protein. It's called myoglobin. It's found in your muscles. And it's going to be most active at a pH of 6. It's going to work at a pH of 5 all the way up to 7. But if we start to move our pH too low or too high, that protein is going to denature and our muscles aren't going to work. And so it's important that the pH levels remain relatively constant. They're not changing that much. But what is pH? Well, we've got to start by talking about water. And so this is a water molecule. Remember, we're going to have hydrogen here, 2 hydrogen atoms, and then 1 oxygen atom. Now, one thing that you need to understand is that this is a polar molecule, and what that means is there's a covalent bond between the hydrogen and the oxygen, between this hydrogen and oxygen as well. And oxygen is really greedy when it comes to electrons. It's going to pull the electrons towards it. And so this is a sharing of electron between these atoms, but it's a polar covalent bond. What that means is since oxygen's pulling the electrons towards it, it's going to have partial negative charge on this side of the oxygen, and then hydrogens are going to have a positive charge on the other side. And so if we were to add another molecule of water, these are not going to arrange this way. And in fact, what we'll have is that they'll be arranged like that. And so the hydrogen atom of one water molecule is going to be attracted to the oxygen of another, and that bond is called a hydrogen bond. A lot of students think that hydrogen bond is in here. No, that's covalent, but the hydrogen bond is going to be between the positive hydrogen, partially positive, and the negative oxygen. And that's why if we have one water molecule and the hydrogens are like positive and the oxygens are negative, and we have another one, they're going to line up like this. And as I pull one water molecule, the other one is going to go along with it. And that's why we have cohesion, and it explains a lot about water. But some weird thing happens with water. Sometimes that attraction is so great that this hydrogen atom will actually become detached from the water, and it'll become attached onto this other water molecule. That would be like me pulling this pinky off and attaching it over onto this other water molecule, leaving me just with this. And so what is that called? This is called hydronium. Hydronium is going to be H3O, and it's going to have a positive charge. What are we left with over here? This is a hydroxide ion. And so what is pH a measure of? Well, the P stands, we think, for the power of hydrogen. In other words, the amount of hydrogen. But it could also be the amount of hydronium or the amount of just free hydrogen ion inside the water. And so if we look at the power of that, or almost the percentage of that, that's going to be what pH measures. And in regular water, distilled water, the amount of this occurring is really, really rare. In other words, it's a 1 in 10 million chance that we're going to have hydronium. And this is really a molar concentration. So to give you a sense of the scale, let's say this hydronium ion right here is represented with this little cube. And so what I'm going to do is pull back. And let's say this is 1 cube and 10 and 100 and 1,000, and eventually what we get, if we scale that, you really can't see that cube anymore. But this would represent 10 million cubes. And so the chances of that one hydronium forming are going to be really, really low. But even though the probability of hydronium forming is low, it actually occurs in water, and it has huge impacts on things that are found within that water itself. And so that 1 in 10 million, I want you to think about that for just a second. And let's kind of add a little bit of the equation of pH. And so some kids get scared by the equation. It's not that scary. So pH, or the power of hydrogen, is equal to the negative log of the hydrogen ion concentration. It's also the same as the hydronium. That's at H3O plus. Those are essentially the same thing. So it's the negative log of that. So it's the negative log, think of this as 1 in 10 million. And this would actually be a molar concentration, but we're keeping it conceptual right now. And so if we take the negative log of that, let's write 1 in 10 million in scientific notation. And so it's the negative log of 1 times 10 to the negative 7. So this is going to be a really small number here. And this is where the math gets really easy. If you were to put this in your calculator, if we take the negative log of 1 times 10 to the negative 7th, what do we get? 7. And so the pH is going to be 7. And this gives us a number that we can actually deal with. And so what does it mean if the pH is 7? It means that the concentration of this hydrogen ion is going to be really, really small. And if we ever vary that, then we're going to be varying the pH.
Okay, so when you... Dang it. I'll go back. My computer, guys, it's not loving me right now. Like, nothing is responsive. It's probably mouse's. No, that's his mouse. Sure. I have nothing. I have no control. I'll just keep watching.
It's going to break these into hydrogen ions and chloride ions. And so you can see here that we're increasing the amount of this H+. And so what is that going to do to that concentration? Now, instead of being 1 in 10 million, it might be as often or as common as 1 in 100. And so if we were to write that as scientific notation. It's the negative log of 1 times 10 to the negative 2. So we would have to have pH of 2. And so depending on the concentration of hydrochloric acid, we could have a pH of 2 or 1 or 3. It depends on how much hydrochloric acid is in there. Now let's look at a base. And so a base, for example, this would be sodium hydroxide or lye. What's going to happen to that when we add it to water? It's going to break apart into sodium ions and hydroxide ions. Now that doesn't help us, remember, because pH stands for the power of hydrogen ion. But what do you think is going to happen to that hydrogen ion that happens to be in the water? Now we've got a hydrogen ion and we have a hydroxide ion, and those are quickly going to combine to form water. And as it does that, it's going to gobble up that hydrogen ion. What's that going to do to the amount of hydrogen ion in the water, or hydronium ion for that matter? It's going to make it even more rare. And so now we have the pH equal to the negative log of 1 times 10 to the negative 12, for example. And so what's that going to be? That's going to give us a pH of 12. And so what does pH measure? It just measures the amount of hydrogen ions or hydronium ions. And bases and acids are going to have different amounts of that. We measure that using a pH scale. And so distilled water is going to have a pH of 7. If we have anything higher than that, that's going to be a base. Anything lower than that, that's going to be an acid. But when you're taking a test, it can be somewhat confusing. And so let's say we increase the amount of hydrogen ions in a solution. So we're going to have more of them. What's that going to do to the pH? It's actually going to lower it, and vice versa on bases. And so watch out for that when you're taking a test. Why is this important? Well, acid rain is one example of that, or the acidification of our oceans is another example. And so this is looking at the pH in the oceans over the last couple hundred years.
Still playing.
And what we see is that our oceans are becoming more acidic. How does that work? You're combining carbon dioxide with the water, and as we increase the amount of carbon dioxide in the atmosphere, that water and the...
Okay, he's just going to keep talking because nobody has control over this man. Okay. So, I don't know what my computer is freaking out about. All right, so you got a glimpse of how the ions look in water. You saw the pH formulas. We're going to practice calculation. The only term that I want to review is the autoionization of water, which is right here. Autoionization means water attacks water. One takes the H+, one is lost, losing it. So that's why it's able to do this. But we'd actually need to balance this blue 2 here. And just in case you didn't notice that, there's 4 H's on that side. There's only 2 there. Okay, so let's go to calculations. Boom, we got this. We talked about this a little bit. Let's go here first. So generally, I'm going to ask you to calculate 4 quantities. pH, pOH, H3O plus concentration, brackets here, brackets mean molarity. Key point to know, okay? So I tell you the concentration of the pure acid is like 2 molar, then you can assume if it's a strong acid, the molarity of the strong acid equals the concentration of hydronium. That's only for a strong acid, SA is strong acid. Same thing for a strong base, molarity equals concentration of what though? Not hydronium here. What do bases make in water? No, don't think conjugates. So acids make hydronium in water. What do bases make in water? Hydroxides. So these are 2 facts that you wrote down on the pH calculations formulas slide. And this is always true for strong acids. Always. 100%. Usually strong bases are going to be exactly the concentration, the hydroxides are going to be exactly the same as a strong base. And I'm going to put unless dibasic. And that's one where we talked about earlier that you need to multiply the hydroxide by 2 because you're making twice as much hydroxide due to that 1-to-2 ratio. All right, so in this one, I'm starting you off saying the hydroxide concentration of an aqueous solution is 6.4 times 10 to the negative 5th molar. That is the hydroxide concentration. And we can literally find everything from this, okay? So hydroxide concentration is 6.4 times 10 to the negative 5th molar. I want you to find the hydronium, the pH, and the pOH. Evan, look at those formulas, and which of these do you want to find first? pH, pOH, or hydronium from this given? Look at your formulas that you have on your paper in your phone book or your booklet. It doesn't really matter which one you find first. You just have to find one where we can utilize the OH concentration. Say again?
Oh, you can find the PO.
Perfect. So I'd like to start with that too, because it's simple. POH's formula is negative log of hydronium. And if you have the hydronium, you just pop that baby in there. You guys have calculators? You know, who has learned about logs in math too? You just got there? Great. We planned this. Or maybe you already know everything about logs. Logs are like an exponential function, right? So I tried to do base 10. Isn't that base 10? That's how logs are written? Okay. So it's really easy when you have something that's base 10. We have something that's, it's not a 1 here that affects this approximate POH, but this should be approximately 4.6. So let me figure out that POH. And when I do want you to plug it in appropriately, okay? So you put negative log, and you'd actually plug that number in here when you're showing your work for me. 4.19. 4.19. So POH is equal to 4.19. Okay, so we've got 2 of the 4 pieces so far. Hydroxide was given to us. We went straight from hydroxide to POH to get the POH concentration. I mean, value. How do I get from POH to pH? There you go. So we're starting to see some of these equations again. pH plus POH is equal to 14. Thumbs up, you were thinking that. Like, yeah, we got POH, we need a pH really easily. Well, if I have this as 4.19, what's pH? 9.81. You can do that math in your head, right? Or just do 14 minus what? Okay, hold on. 14 minus the pOH will give me pH, so I'm rearranging this formula, and that is equivalent to me doing 14 minus 4.19, which would be 9.81. Okay, so guys, right off the bat, you should be able to tell me from the pH, you should be able to tell me, is that acidic or basic? Say again? Okay, before you make your comments, I heard both still. You have this pH scale that we work with. From 0 to 14 is generally how it's described. 7 is neutral in the middle. 14 is basic. And 0 is acidic. It goes alpha order, okay? A to B, acid to base. Cannot get that mixed up, okay? Which side do you think has more hydronium? Hydroniums, think about what formula is that? H. Hydroniums win on this side. Okay, there's a lot more hydroniums, which are the acidic portions. On the acid side, what is there more of on the basic side? Hydroxides. Okay, so we're going to be using these H words a lot. You got to remember, be able to visualize them and associate them with acid or base. Hydroniums win on the acid side. There's a lot more. It pulls the pH way down. Why does it pull the pH down? It's because it's got that negative in front of the log, which makes it decline. Okay, so 9.8 falls on the basic side of things, so that should be basic. And then you're like, oh no, you can't really tell that from there. You can a little bit, but not really. Okay, let's get our last quantity. So what are we still missing? Hey guys, we're missing hydronium. I heard it. Okay, so if I'm missing hydronium, what was the equation that took pH to hydronium? You just wrote this down. You just wrote this down in your notes. You guys should be like looking at your little pogables. Antilog, okay, I'm hearing. Antilog of what? Of the negative pH. There's another way to do that though. Antilog, some people have on their calculators, other people don't. The antilog is the same thing as going 10 carat negative pH. Okay, this is the way you'll see me write it on my notes, and that's how I solve with my calculator, but I want you to pick up your calculator, try this right now. I want you to put in, to solve for hydronium, 10 to the negative, what's the pH again? 9.81. What'd you get, Matt?
5, 4, 6, 8, 5, 2, 3, 4.
Do I have a exponent? Times 10 to the... Heck no. Give me something else.
Yeah.
Chase, tell me. Okay, one. Good job, Matt. Chase, some of yours.
5, 4.
Times 10 to the -10. Okay. And guys, this is a concentration, so you need to put molar afterwards. All right, those of you not actually writing down any of these notes, I hope that you can do your homework without me, or you can rewatch this video in your own time. Okay, so you got how to solve from one quantity. You can solve for 4 different things, right? Let's do another one. Let's start with this acid. Okay, so we have nitric acid. Think real fast. Is nitric acid a strong acid or weak acid? Strong, because you know your 6 strong acids, right? Mm-hmm. What's formula for nitric acid? HNO3. Okay, what is this telling me? I know it's telling me the concentration of nitric acid. I got that much. But what's important about that? It's equal to H hydronium, right? Okay, that's because strong acids 100% ionized, and so this nitric acid makes hydronium and nitrate. But who cares about the nitrate? We should have hydronium part. Okay, so that's the reason why I'm just making this assumption off the bat. If it's strong, it 100% ionizes. It makes whatever this is the same as the hydronium. So 1 of the 4 have been solved for. Done. What do you guys want to move to next? Using that quantity. Look at your formulas and then make a choice. Let's go straight to pH, right? Does everybody see that pH is super easy? Because it's negative log of the hydronium. And you're like, got hydronium, plug that baby in. So negative log of 0.75. Wait, what? 125. So it's so easy to think about the pH scale. There is such thing as a pOH scale, but why think about the pOH scale if you can think about the pH scale? Because we've seen the pH scale before. We know it ranges from 0 to 14. It actually ranges from like negative something, negative 5, to like 20. Those are called super acids, super bases, if they're on either side of the 0 and 14. You'll see some negative pHs in your homework. Don't be scared. That's because they're super acids. They're very, very concentrated. Okay, so this is going to be obviously very wet. Acidic. This is on the acid side, right? It's very, very acidic. Okay, so we've got pH, we've got hydronium. Let's use that formula that we haven't used that increments hydronium and hydroxide at the same time. So hydronium is equal to, or hydronium times hydroxide is equal to what? Okay, this is called the Kw constant. 1.00 times 10 to the negative 14th is called the Kw constant. This is an equation that you can use to get from hydronium to hydroxide because it's the equation that utilizes both of those, and the constant, of course, is given. So if I want to solve for hydroxide, what do I do? Divide by hydronium. So when you divide by hydronium on both sides, you would then be plugging in numbers of what? So this cancels on this side, of course. You would then be saying hydroxide is equal to 1.00 times 10 to the negative 14th parentheses divided by what? Nope, no, no. 0.75, right? Labeling this work is going to be very helpful because you know you're solving for 4 things. It does get kind of jumbled up. So this is hydronium, so we're putting that in the denominator. 0.75. And then calculate from what you guys get for hydroxide. Negative 14, something like that.
Yes.
Molar, because that one is a concentration. Because brackets mean molarity. So what's the last thing we need to solve for? pOH. I want to do that directly from what? Okay, you could do that. So I got one side going, let's take, this is the pH, right? You could say pH plus pOH is 14. Or you could do what? So this is OH, right? So you're saying pOH is equal to negative log of OH? Is that what you're saying?
Yes.
You can, oops. So that means just plug that in there. Either way will work. So tell me what your pOH is. 13 point what? 88. Let's go 88. And that makes sense because this is a really strong acid, so the pOH is actually going to be very high. pOH is not really a number that we generalize. it's easy to generalize the pH because they can recognize that's a strong acid. Okay, so I'll leave that back down there for you guys. On yours, here's a little longer, sorry. Look at the ones that say homework, pH calculation, strong acids, and base. I want you guys to do A through F, and then that secondary question on the bottom. So that's actually what I want you to do. You can do it now or do it later.
Attention, any staff that wanted to partake of the wonderful lunch that was provided today in the media center. If you have not already done so, please go to the media center now. Thank you.
So I'll just say pH folks. That's it. If you would like to start PS19, do you see that I printed it for you as well? And what I'll do is, I need a fourth period a little bit different than y'all, so I need to catch them up on something. So next Tuesday, I actually have to work for the county. I won't be here next Tuesday. I'll leave a day where you guys can just work. If it's on Mythbusters, if it's on ABCs, if it's on concepts. So next Tuesday for sure. If you want to bring your book or something to help with that, then make sure you do that. But right now, for sure, start your pH calculations. Unless you just want to get home and you want to do something else right now. Oh, finish your notes. Yeah, if you didn't finish your notes, go back and finish notes. On these two, but then look on the bottom. Start off with the pH in those. Yeah, so you're talking for all. Yeah. I just want Okay, so work on pH calculations, or on your problem set 19A, or on chemistry, something related.